We're now ready to look at regular languages from the standpoint of formal language theory. Formal language theory is the study of languages as mathematical objects, strings, sets, and what formal apparatus can and can't generate what string sets and what properties the string sets have. So to give that a little bit more specificity, recall that we start with a set of symbols, which is finite, sigma. Sigma star is the set of sequences of such symbols that is possible of length 0 or greater. So a length 0 string or sequence of symbols is the empty string. A singleton element from the symbol set is just a length 1 string, and so forth. A language L is a subset of sigma star. So it's just a set of strings from the symbol set. And we can talk about when there's a formal apparatus like a regular expression or a finite-state automaton that matches or accepts a set of strings. The set of strings that is matched or accepted is called the language defined by that formal apparatus, in this case a regular expression or finite-state automaton. Now, importantly, any language that is defined by a regular expression or finite-state automaton is a regular language. And what makes this more than nomenclature is that we have another way of defining regular languages, which is inductive. The inductive characterization will start off with the base cases. First of all, the empty set is a regular language. Any singleton that is a single element from the symbol set sigma or the empty string, any singleton like that is also a regular language. And if we have a regular language, we can talk about other languages that are then regular. So in particular, the complement of the language is regular. So the set of strings that is not in a regular language is also a regular language. And the Kleene closure, the set of sequences of strings from a regular language, is also regular. Furthermore, if we have two languages that are regular, we also say that their concatenation, that is, the set of strings that are concatenations of a string from L1 and a string from L2 is regular, and their union is regular. And at this point, I recommend that you go back and look at how we characterized regular expressions, and because the way that we defined regular expressions in terms of the syntax and semantics is closely related to this inductive characterization of the regular languages, which is why they wind up defining the same string sets. At this point, it's also useful for us to talk about how to go between regular expressions and finite-state automata. So to construct a finite-state automata that corresponds to regular expression, we start off with base cases. So one base case is when the regular expression picks out only the empty string. And that's a very simple automaton that has one state, the start state, which is also a final state. So it will not accept anything with the empty string. The second case is when we're talking about the empty set, which is characterized by a one-state automaton that has no final state. And then the case where the regular expression matches only a single element from sigma, call that element without loss of generality A, we have a simple automaton which has two states. The initial state is not the final state, is not a final state. The final state is transitionable from the initial state, with the transition taking as input that single symbol. So those are the base cases. And the inductive construction requires three different kinds of operators: concatenation, disjunction, and Kleene closure. And these little shapes are generally for automata, whereas the circles once again are states. And so we have to give some semantics to what it means for these diagrams to have an arrow pointing to or from an automaton rather than a state, because an automaton, of course, in general is a set of states. So the idea here is that we would construct a finite-state automaton that corresponds to, say, the concatenation of two automata A and B by creating a new automaton that has a state for every state in A and a state for every state in B, and then we link between the two with the following semantics. So saying that an automaton is a start means that the resulting automaton that is constructed by this operator will have the property that the start state from the original automaton A will be the start state in the new automaton that's constructed. If we talk about an automaton we designate it as being final, that means that the resulting automaton has a final state that corresponds to every final state of the original automaton. An arrow from an automaton is taken to be an arrow from every final state in that automaton, and an arrow to an automaton is an arrow to the start state of that automaton. So if you actually run this through, then you will get automata that satisfy concatenation, disjunction, and Kleene closure. Okay. Notice that we don't have a we don't actually have all of the set theoretic operations that correspond here, but we can talk about them in a little bit greater detail. And I want to just end this little segment by pointing out that we have some closure properties of regular languages. So although there's a finite state model implementation, there is also an abstraction where we don't actually have to think about the automata themselves, just about the properties of the languages. And from the past two slides, we saw that regular languages are closed under concatenation, Kleene closure, union, and complementation. It turns out that there's another important property that they have, which is closure under intersection. And I'm not going to explain this to you here. I'm going to give you as an exercise, try to figure out why this is going to be the case from everything that we've covered. This is going to be important going forward. And so remember these closure properties of regular languages.